Hi Rob, excuse me. I can propose, we have a little problem with the recording the session, but I can recording the session with a software from my PC. That's okay for you?
That should be fine, yeah.
Okay,
Yeah.
then I will share the video session. That's
Yep.
okay? Okay. Yeah. Um, it's ready.
Es por Bluetooth. Conectar. ¿Todos se pueden desconectar de su Bluetooth? Porque no anda interfiriendo. Okay.
Okay, so you guys are you ready?
Yeah, we prepare a
Okay.
little presentation.
So yeah, if you have a presentation that you want to follow, go ahead. We can start with that, and then we'll use the webcam or a camera to look at to go over the rocket from the nose cone on down to the tail end.
Yeah. Okay, we're gonna start. Well, first, good afternoon. Thank you for being here with us. We are the Condacova Rocketry Club team. My name is Odalis, and I am the team lead in this edition of the Spaceport America Cup. We present a new mission. It's named the Xolos Coco Rocket. Is a rocket made with natural fiber-based composed materials, just like last year, and the general characteristics of our rocket. Well, this is the rocket overview. The length is 121.6 inches. The total weight is 44.1 pounds. The reference diameter is 6.7 inches. The apogee target is the 10,000 feet maximum velocity with 1,719.4 feet per second. Center of gravity at 83.46 inches, and the center of pressure to 93.7 inches, and the motor is a GOTS category, is the Aerotech and 8045 NT. And well, we use the natural fibers. With these fibers, we have experimented with various configurations through this research to determine the most suitable combination for the different needs of each part of the rocket. The fibers are coconut, jute, and anacan, and these are the configurations that we use in our rocket. First, for the body tubes, we use the configuration to coconut jute to 60-90 degrees. For the fins, coconut jute 60-19 degrees, and anacan with 19 degrees, in addition to an extra layer of fiberglass for the fins. And well, the aerostructures team will present the more of this material. And this is results with our tests.
Hi, I'm Dario, and Aerostructures and Materials team lead. I will go present the general points of this team. Number one, the airframe structures consist of 6 main parts. One is a motor body and tubes, fins, nose cone, bow tail, couplers, and rail buttons. Each of these parts will be reviewed individually, explaining their respective manufacturing process. Before going into detail, it is important to mention that all the components of the fuselage were manufactured by hand using an industrial-grade epoxy resin, which was decided to be used due to the results obtained in the tensile and resistance test that we carried out the different types of configuration of our fibers based on the ASTM V3039 standard. These configurations are mainly one layer of coconut fiber, two layers of jute, one at 60 degrees and the other at 90 degrees, with a tensile strength of 1,238 pounds force. This for body tubes and couplers. And another configuration is one layer of coconut, one layer of Enequén, and two layers of jute at 19 degrees and 16 degrees, with a tensile strength of 1,044 pounds force. These four fins.
Right, so let's talk about the motor body and tubes. The rocket's fuselage was designed in such a way that it could meet the requirements of the mission. Therefore, the fuselage body was divided into three main parts, and I'll start explaining them from the lowest part to the highest one. The first part, of 39.37 inches, was intended for the placement and fixing of the fins and the motor tube. Then, the second one, of 23.62 inches, to the payload support, and the last part, of 27.56 inches, to the recovery system. In turn, the motor tube of 24.8 inches was made of two layers of fiberglass with an epoxy resin matrix due to its thermal resistance and lightness. Now, we have to mention that the thickness of the three tubes is of 0.2 inches, and the three of them, the first three, they are covered in an orange gel coat, which serve the purpose of really sealing the pores that the epoxy resin may not have reached. So we really make sure that the rocket is completely safe and has the right endurance.
Hi, can you hear me well?
Yeah.
Okay, so my name is Daniel Gomez and I'm the launch leader, and right now I'm going to explain you a little bit about the fins and the way we attach them. The fins are considered the second most significant part for drag generation over the rocket. So because of this, and considering the fin flutter effect, which is going to be reviewed later, we decided to add an additional layer of fiberglass over them. Now the fin flutter analysis shows us that the flutter velocity is 1,340.35 feet per second. Considering that the maximum speed that the rocket will achieve is 1,079.4 feet per second, we are nearly 300 feet per second below the fin flutter effect. Now it is important to mention that the fins have a narrow shape with a thickness of 0.28 inches and a root core length of 7.87 inches, and they are 120 degrees separated by each other. Now let's talk about the way we are going to attach the fins to the motor tube. For this, we will use two aluminum strips for each fin that are going to be screwed to the root core of the fins on both sides using 6 5mm screws. The strips are designed in such a way that they could be inserted into the slots located in the centering rings, which are 0.4 inches thick. Once the fins are assembled to the motor tube and the centering rings, we add an additional layer of fiberglass using the tip-to-tip method to reinforce the whole assembly. And right now you can see the exploded view of the assembly of the fins.
Right, so now let's talk about the nose cone. Since most of the time the rocket will be in a transonic mode of 0.72 Mach, we decided to use a nose cone that takes the form of the hack series. specifically the von Karman nose cone, due to its ability to reduce aerodynamic drag. We used Allens-Whitcomb formulas to determine the drag coefficient in the von Karman nose, which gave us a value of 0.4407, which is close to that obtained in ANSYS, with a value of 0.4743 considering 0.72 mech. It was made with one layer of coconut fiber and two layers of jute fiber at 60 and 90 degrees. It has a length of 25.2 inches and has an outer layer of fiberglass as reinforcement. The shoulder length is of 3.94 inches.
Okay, so now let's talk about the bow tail. So due to the drag generated at the base of the rocket, we decided to add the bow tail to the fuselage to reduce the magnitude of these aerodynamic effects. The bow tail has an outside diameter of 6.69 inches and a length of 7.01 inches. It features a 3.15 inches shoulder that will attach the bow tail to the fuselage using 5mm screws. The bow tail was made of natural fibers such as jute, as well as an outer layer of fiberglass. It was designed to be frangible in order to decrease weight at high altitudes and also to ease the removal of the motor case once the rocket is recovered. So in order to determine the measures of the bow tail, we made an analysis of bearings using Excel to define the ideal size, reduce drag generated, and thus increase the overall performance of the rocket. It was decided to create a multiple linear regression model of the different target variables to try to predict intermediate cases from randomly generated tests in OpenRocket, with the goal of selecting the ideal bow tail design. Once the models were obtained, the cases were optimized to achieve the highest apogee with a stability of 1.69 cal and the required exit speed. The multiple correlation coefficient obtained, being very close to 1, indicates that the variable changed in proportion, and also that the coefficient of determination R2, that is also very close to 1, indicates that the model is very effective in predicting the apogee.
Now, for couplers, due to regulations for adding couplers to rocket joints, it was necessary to design them in such a way that their length is equal to 1.5 times the diameter of the body tube. The fuselage has two couplers, one of which will attach the body housing the engine tube and the payload tube, while the other will link the other end of the payload tube to the recovery system tube. Now let's remember 20.1 inches for recovery and 10.53 for payload. The first coupler of payload shall be attached to the fuselage by a thread and screw system for both the top and bottom. The manufacturing material is aluminum. The second coupler uses a system of screws and nylon pins only, but only so that the top part remains fixed to the body tube of the recovery system, while the lower part is fixed by safety pins to allow the deployment of the recovery system. Its manufacture is the same as of rocket tubes. Now, for rail buttons. The rocket has two rail buttons. Each of these are type 1515. These are located 24.6 inches from each other, and they start at 7.48 inches of the base from the fuselage.
Okay, so now let's talk about the stress concentration analysis that we did. So we did an static structural analysis using ANSYS Workbench, which objective was to determine the reliability of the aerodynamic structure against possible structural failure. So all the technical information of the used materials was added to the simulation, where we defined the centering rings, the motor and its container being made of aluminum, while everything else are composite materials. The analysis conditions that we established were a distributed load on the exit of the nozzle to simulate the thrust generated. Also, the top of the rocket was fixed. And once we run the simulation, we found that the maximum stress was nearly 6 megapascals, while the maximum tensile strength of the composite materials used is 19.7. This means that we have a safety factor of 3.28, So as a conclusion, we can say that the structure will not tend to fail during the whole flight.
Okay. Hi, Rob and Tony. Nice to meet you, and and I'm very happy to be here and talk about our project. And now I will to talk about the fin flutter a little bit, and additionally, other analysis was performed. Um, well, as my partner Daniel mentioned, the flutter velocity is have a flutter velocity of 1,340 feet per second, and the maximum. Well, this is pretty nice number, and compared with the with the rocket's designated maximum speed is the 980 feet per second, and suggested that maintaining significantly lower speed, that the flutter speed reduce the likelihood, reduce the probability of encountering this phenomenon as fin flutter. But additionally, we perform a modal analysis test in ANSYS Workbench, and with the intention to get and know the fins behaviors, and we get the 20 shapes modes to know about of this, and even we know the natural frequencies. Well, that's one of the that 20s, and the other one, and the other test, we to complete this analysis, we use a drag test in ABL with the configuration of our fin, and in different run cases, like different cases of flight and different velocities, different numbers of Mach, to know about of behavior of our fin. And that's all about the aerostructures. And now we'll talk about the recovery subsystems, recovery and controls.
Hi, the recovery subsystem, the deployment method of the parachutes entails the implementation of a pyrotechnic mechanism, and it consists of two explosive stages. These explosions are controlled by two flight computers. The primary is a commercial flight computer, and the redundant is an Israel flight computer. It's important to know that each flight computer is it's independent.
Hello, I'm Ricardo, and I'm the control systems team lead, and I'm going to talk about the flight computer. For the commercial flight computer, we are using the RRC3 Sport altimeter from Missile Works. We choose this computer because it is very easy to configure and use, and also we have previously employed it before, and we have conducted various tests with it. On the other hand, the Strat flight computer is designed from commercial components such as the sensors and or the development board. Its logical programming is the flowchart is shown next, and the flowchart is basically a set of if sentences that goes through each task until it completes the duty. Additionally, it has a startup sequence where the detection and proper initialization of the sensors are first verified. Then it continues with an igniter detection sequence, and finally, when everything is in order, the launch phase begins. Following the evaluation guides, we employ noise filters. Noise filters were implemented in the accelerometer and the barometer measurements. Tests were conducted to assist measurements, response, and filtering level, selecting the filtering constant that best suits the required filtering speed. The main apogee detection will be performed using the accelerometer. We choose this because this option was deemed more suitable due to the possibility of the rocket reaching transonic speeds, which could result in inaccurate altimeter readings at this point. So far, several tests have been conducted to assess the variability of response to apogee, data collection, and information processing. It is planned for next week to test the computer on a L1 certification rocket modified for dual deployment, in which the computer's operation will be verified. In the event of any failure or unexpected circumstance, the option of using two commercial computers will be considered.
And the recovery rack architecture is the following. We have 2 disc or covers, 4 powder charge containers, 2 U-clamps to attach the main shock cords, and washers and spacers. And in the middle we have a case for the electronics.
Okay, now we'll talk about the tight deployment charges. Okay, we'll use a black powder deployment method, and for the main flight computer, which is the SRAT, we'll use for the main we'll use 5.2 grams of black powder, and for the redundant, which is the cost, additionally 1 gram in that one. And for the drug parachute, we'll use 4.2 grams for the main, and 5.2 for the redundant.
The drug parachutes both will be commercial, and for the drug we will be using a 24-inch elliptical parachute manufactured by Fruit Shoots, and the deployment altitude will be 10,000 feet, and the expected descent rate will be 90 feet per second. And the main parachute is manufactured by Sky Angle. The surface area will be 89 square feet. The deployment altitude that will be programmed in the main flight computer is 1,500 feet, and the expected speed descent rate is 26 feet per second. The short cords and attachments, we will be using quick links and swivels. The length of both short cords is 30.41 feet, and the width is 1 inch. And to protect the parachutes, we are using an Nomex Parachute Protect. This to prevent the contact with fire on the explosion.
Hi, nice to meet you. I'm Rebecca. I'm one of the co-leaders of the avionics and payload team, and we're going to talk about the global position system, our CubeSat that has 3 units, and the PCBs and sensors that are going to be inside our rocket. So first, for the GPS, we are using the COTS featherweight system, which has a track frequency of 923.8 megahertz, a tracker serial number of 2618, the ground station serial number that is 3030, and the tracker is going to be located in the nose cone to reduce the interference with any metallical objects that are in the fuselage. It will be held with endless rod to the nose cone point. So the ground station works with the LoRa protocol, and the data is sent via Bluetooth to a cell phone that works with iOS. it can be connected to more than one device. Some of the data that we're going to be receiving is the latitude, longitude, altitude, the tracker's battery voltage, and the number of tracked satellites that are connecting our GPS to our ground station. We did some functionality tests, such as horizontal distance test, vertical distance test, interference with the composite material that we're using, and with the spare antennas that come with the package. So we can see if with different conditions it still works adequately, and it did so. They were good functionality tests.
Hi, my name is Monica, and I'm a member of Avionics and Payload team, and I'm going to speak about the CubeSat. Well, the payload consists of a 3-unit CubeSat nanosatellite. The dimensions of each unit are 10 by 10 by 10 centimeters, and the total dimension are 10 by 10 by 30 centimeters. And it has a mass of 9.4 pounds. Well, the structure of the CubeSat consists in a rectangular prims, which have 3 units in all the prims. The lower unit, we include the 2 rechargeable 9-volt batteries, and the second and the third units include the PCBs that we are going to explain you next. And the structure of these levels are holding with 2 bases. The bases are this one, and these are from PLA, and the bases are going to be holding to the CubeSat with 8 screws, M4 by 0.7 with a strength of 3 millimeters. And well, the reason of the design of this CubeSat is because we want to reduce the use of screws in all the structure. So the only way that we see that we can resolve this one is using only a structure, and we use only a kind of movable plate. That this plate is going to be holding to the another structure with 4 screws, M4 0.7 with a strength of 10 millimeters. Okay, and the next is that all the structure is going to be welding, and only the movable plate is going to be holding with the screws. All the design is based in a Mexican norm about design and manufacturing CubeSats. And to join the CubeSat to the fuselage, we decided to use a circular PLA base that also have another circular base from steel, and that it's going to be holding to the fuselage with some screws through the diameter of the fuselage.
Okay, my name is Braulio Alvarez. I'm part of the avionics team. I'm the co-leader of the avionics team, actually. And I'm going to explain to you the 2 PCBs or payload of the CubeSat. Well, we use 2 main PCBs that each of them read some different variables. We're going to talk about the first PCB. Well, the first PCB is going to read environmental variables like pressure, like humidity, air quality, and it will work with a Raspberry Pi Pico, and it will have a telemetry module like the XB Pro S3B, and it will be energized with a 9-volt battery. This battery, we're going to talk about these batteries later. Then we have the second PCB in the second level. The second PCB is the inertial measuring unit. This PCB will read accelerometer, is a magnetometer, and a gyroscope, and a GPS for a longitude and latitude variables. These two PCBs are working, as I said before, with a Raspberry Pi Pico microprocessor. Both PCBs have its own micro SD module, and its own regulator, because it both work with 5 volts. And then we have the third unit. This third unit will be the batteries. Will be 2 batteries. One battery will be in each PCB. This battery is made with nickel metal hydride, so we avoid the provision about the battery's material. And that's all for the avionics.
¿Quién sigue? Pues si quieres, que si tienen alguna pregunta, si quieren, ¿qué es lo que quieren ver del cohete?
I do have a couple of quick questions before we look at the rocket. Can you guys hear me okay?
Okay.
Okay. I've got a couple of quick questions regarding, before we look at the rocket, the launch detect methods. You're using the accelerometer on the SRAD flight computer to detect launch. Is that correct?
Yes.
Okay. Can you just describe a little bit about what parameters have to be met before you detect launch?
¿Qué te pregunto? ¿Qué es lo que...? Sí.
Okay, for the SRAD computer, we have a launch detection system that is barometric. After the initialization, the barometer is waiting for an arming sequence where we have a safety altitude for prevent any accident explosion. And after the safety altitude, the computer start to work in the protocol established before the protocol I mentioned.
So, and I hopefully this makes sense, but are you looking for a change in altitude to determine launch, or a change in accelerometer to determine launch?
For the altitude.
Okay, what kind of altitude change are you looking for that says, hey, we've launched the rocket?
Well, it can be set the altitude, but normally, for example, for the RRC-3, the launch altitude is from 50 feet.
Okay, but how about your SRAD computer? How are you detecting launch on the SRAD?
We can set the same altitude from detecting the arming.
Okay, so it is based on altitude. Okay, and you've tested that so that if it's on the pad and it's windy, the wind doesn't cause any false triggering of the launch detection system?
The filters we implement is from noise as the movement of the rocket, and for wind noise. And for example, I saw that for transonic speeds, the barometer can fail in the measurements. So we prefer to use the accelerometers for detecting the apogee. And it's
okay.
Well, we think it's a simple election.
Okay, so I think you'll be okay because you have the RRC3, which uses, of course, altitude. But one issue to think about and to consider when you're using an accelerometer to detect apogee is that the rocket, once it starts going, it doesn't really know if it's going perfectly straight up or sideways. And if you get a lot of horizontal velocity, that can delay or change its ability to detect altitude or apogee correctly. So that's something to kind of consider if you're just using a straight, if you don't have any kind of way to detect the change in angle, it's hard to just rely entirely on integrated altitude and for change in G. But I think you'll be fine because you have the RRC3, which is very reliable. So I don't think that'll be an issue, but you're going to want to carefully compare after the flight the apogee your flight computer detected versus what the RRC3 detected. And now I saw the all thread, and we can get to the all thread when we look at the rocket. The other question I had is you printed a lot of the parts out of PLA, and I don't think it's going to be an issue because they're internal, but they are supporting a significant amount of weight. The rocket wing or the CubeSat, which is normally not really part of my concern because it's not being ejected from the rocket. My real goal is to make sure the rocket flies safely and recovers in one piece. That's my goal. But a concern that I think you need to think about is PLA deforms under heat pretty easily and it loses its strength. As a test, I printed some fins, a fin can out of PLA, and I live in Texas, and I just put it out in the sun. And it literally, the fins deformed without any stress on them at all. The sun in Texas and the heat in Texas is enough to cause PLA to basically just melt. It doesn't really melt, but it softens and it will deform under pressure. So that's something to keep in mind that when you get to New Mexico, the temperature is very hot. It's an enclosed space and you have 9 pounds of force all in. So if that, the parts may deform just sitting there in the heat. In the future, and I have nothing against 3D printers. I use a lot of 3D printers, and I do a lot of stuff, but the appropriate material is important. And I don't use PLA at all anymore for anything that's outdoors. I always use at least PETG, which is a little more difficult to work with, but it's much better at withstanding the heat. And it's a little stronger. If it's printed correctly, it actually can be a little stronger than PLA. So I don't see that as a concern for this time. I don't anticipate any safety issues, but just going forward, as you guys work on this for next year, you might consider switching to PETG or another alternative other than PLA. PLA is great to print. It's super forgiving, but unfortunately, it and the summer sun don't get along too well. So I just wanted to kind of bring that up, but I don't think it's a safety issue, so I think you'll be okay. The other question I did have was, and I don't remember if you guys need a ham radio for the XB telemetry module, or a ham radio license.
The first question that you said that you don't recommend to use PLA. Actually, it's good to know that the PLA is just the base, and we put two steel plates between, in the top and in the bottom.
Okay.
They are supporting, and the PLA is just the base.
Like the fins.
Okay. Sounds good. And if you guys have worked with it before, and especially in hot temperatures, you'll get a feel for how it responds, and so hopefully it'll be fine. And again, I don't see it as a safety concern. I just wanted to kind of point that out.
Okay, thank you.
And then the other question was if the XB Pro requires a ham license, and if it does, do you have someone on the team that has the ham license?
No, we are using the Featherweight and the XB, and neither of them need a license because they already come with a commercial one, so it isn't needed.
Okay. Perfect. All right, so let's take a look at the rocket. If you guys have a mobile camera or whatever, we can start at the nose cone, and we'll just kind of work our way down.
No te creas.
I know it's kind of a pain, but it is. And you've answered a lot of questions that are on my sheet, and I think I sent you guys a copy of the sheet before so you can kind of be prepared. And you've answered a lot of those questions already, but I do want to see I want to definitely look at the shoulders and just the attachment points and all that good stuff on for recovery.
A ver, ¿puedes hablar? Vénganse por acá. ¿Alguien que agarre el micro? Si quieren, ahora sí apaguen todas sus cámaras.
Está apagado este micro, ¿verdad?
No sé.
Uh-oh.
Voy. Okay. Starting from the nose cone?
Yeah.
Okay.
We only have about 10 minutes left, so hopefully, I think we can get this done.
Yeah. Okay. So this is the nose cone. As you can see here, the tip is flat. So it won't be like that. The tip will be of aluminum. It is still being manufactured, but we will have it by next week. So this one is the tip, and it will have a aluminum rod as well that will connect it to the base of the featherweight.
Okay.
So next we have the body tubes. This is the upper body tube, and this one will be in charge of the recovery system. This is the other tube, the middle one. This is in charge of the payload support. And this is the last one, which is for the fins and for the motor tube, which will be inside.
Okay.
Also, for the couplers, they are, as well as the tip of the nose cone, being manufactured. We will have them by next week. And to end this, we have the rail buttons. We like to attach them by the very end of the making process of the rocket. So yes, but we will use these exact ones. I remind you, type 1515.
All right. So can you pull the nose cone out of the rocket there, so I can just take a look at the shoulder and the attachment point on that?
Yeah. So here it is. And as I mentioned here you can see a little bit of a hole. Here it will go the aluminum rod, and it will get attached to this part.
Okay. How heavy is the nose cone?
How heavy is it? Around.
Just roughly.
8 pounds. No. Sorry. The conversion.
Well, you can tell me in kilos. Kilos is fine.
8 kilos? 2.
Yeah.
2 kilos.
Okay, that's good. Now, can you show me where that?
Sorry. No. Sorry. 800 grams.
No, it's more than it's got to be more than 800 grams.
Yeah,
but,
sorry.
So show me the end of the nose cone. Take it out again, and I want to see the connection that holds the. Yeah, that I want to see. Can you get closer to the connector on the end there?
Well, it is provisional. We will change it for a U-clamp.
Okay, that's what. Yeah, because clearly that would not be suitable at all. It doesn't look like it's robust enough, and those edges would cut through the cord, and so when you will definitely need to replace that with a suitably rated U-bolt. It doesn't have to be, because the nose cone's not heavy. That U-bolt or whatever doesn't have to be 1,000 pounds. It just has to be suitable for the weight of the nose cone.
Well, that's provisional for the rack. We are using that, and we will be changed for one of these.
Okay, perfect. Looks good. In fact, here, while you've got that, let me take a look at the rest of that there.
The rest of
Here
we have.
I just want to see. So you have the all thread goes through the entire thing, and can I see how the all thread is the ends of the all thread? I want to just make sure that you have washers on the end of that. Yeah, there you go. So okay. Make sure that you've got suitable sized washers and lock washers on between the nut and the plate itself, just to kind of spread the forces out. And I can't quite tell. Yeah, so like on that end, make sure that you have
but a washer will be here and here, and in the other side as well.
Yeah, okay, not so much on that, but on the all thread, on the two pieces of all thread, I can't quite tell if there's a washer on those. It looks like there is, yeah, on that. So make sure that you have a suitably sized washer on that and a lock nut or something so that it can't come out, right? Because that's one thing that in the safety inspection, when you're there, they're going to want to make sure that you have a good load distribution by having a suitable washer, and that it can't, come unscrewed in flight somehow. So those are the things that you want to make sure that you've got set up, before you leave, so you're not stuck with that there. And if you would flip it around, just let me look at the other end. Okay, looks good. Yeah. Now, do you are both charges in that same charge cup, or tell me about how your ejection charge is?
We will use 4 charges, but actually we just put 1. But it will be 1 here and 1 here.
Okay.
Each
Okay.
one for both flight computers.
Okay. That's good. I just wanted to make sure they weren't in the same
Yes.
thing. Okay. All right. So now let's. Can you separate where the rocket is going to come apart when the main deploys?
Yes. Here,
Okay.
the drag chute is in that side, so it will be
Okay.
first deployment, and the second deployment consists in the separation of the nose cone, and here is the main charge chute.
Perfect. Okay, that's fantastic. That's one of the main things I noticed I had on my notes from before was the coupler length, and the coupler length looks great. Really, very good. Let's take a trip down to the back end of the rocket where the nose cones are, or I'm sorry, for the fins. It's telling me we only have 7 minutes left in our meeting, and I think we can get it done in 7 minutes, but otherwise we'll have to have a quick follow-up. Now, do you have the fins assembled? I don't see them in the rocket, and I see the motor case. Or if you can just show me one of the assembly.
Can you hear me?
Yeah.
Right now we have a sample of how the fins are going to be assembled. As we mentioned in the presentation with the exploded view, the fins are going to be attached with this aluminum. Well, we're going to use aluminum strips. They're going to have 6 perforations, which are going to have 5mm screws. The aluminum strips are designed in such a way that they could be inserted in the center rings, which is going to be made of aluminum. And the center rings are going to be 0.4 inches thick.
Okay. And then I think you mentioned that you were going to do, once you had it in, you were going to put fiberglass over that as well.
Yeah, once all of this is assembled, we're going to use the tip-to-tip method to reinforce the whole assembly.
Okay, that looks really good. I think even though it's not completely assembled, but I will tell you that when you guys are at the contest and you're in the safety room, the number one thing that they're going to do to test your fins is they're going to grab the end of the fin. Hang on, let me just zoom out here for a second. They're going to grab the end of the fin and bend it really hard. They're going to put a lot of force on that fin. So when you guys are done, you need to make sure that if I grab the end of the tip of the fin, and here's the body tube down here, that when I try to bend that fin, we don't want it obviously to do that. That's no good, right? But we also don't want to see any flexion or very little flexion from the tip to the bottom. I mean, it ought to be like, I ought to be able to like push on it very hard, and it ought not to move, really at all. So when you're assembling that, make sure that that when someone like me gets a hold of that fin, or Rob, whoever it is, and we're pulling on it, that the fins are nice and sturdy and aren't going to move, because that's the number one fin failure that we see at the safety briefing. And then people have to put additional layers of fiberglass over it, and obviously when you're there, you don't want to do that. So make sure before you leave, if that takes an extra layer of fiberglass or whatever, or some fin fillets, just make sure that those fins are super stiff and aren't going to either do this or aren't going to move like that. And since it's not it's not completely done yet. You're going to be on your own to make sure that you get there between now and when you show up in New Mexico.
Yeah, actually, last year that was one of the first tests that we did when we assembled the whole structure of the fence. That we take both fence and we try to bend just to confirm that there's no bending, that they maintain fixed all the time.
Perfect. Okay, last quick question is motor retention. How is the motor held in the rocket?
Okay, so
Do you have like a...
Okay, so we have the motor casing over here, which is going to be inside the motor tube, which is made of fiberglass, and it's going to be held with the truss plate and the bottom closure that comes with the hardware of the.
I thought I saw an aero pack retainer, you know, an aluminum thing that holds the motor in.
Yeah.
In other words, I just want to, okay, that's what I wanted to see, to make sure that you have something that keeps the motor from falling out, and that's perfect. Okay, because that's the other big issue is teams sometimes don't have the motor very well retained, and that's hard to kind of fix after everything is built. And I just wanted to verify that you did have that ready to go. Excellent. Okay, give me just a minute. Let me look over all my notes real quick and make sure I haven't missed anything critical here.
I think you're muted, bro.
Tony, you mind if I ask a question while you're looking at your notes?
Go ahead, Bob.
Guys, can I see your boat tail for a second? Now, is the end of the motor tube going to be at the far end of the boat tail, or is it going to be up snug to the base of the rocket?
Uh-oh, we're not hearing any audio.
There's no sound coming out, guys. There we go.
There you go.
Yes.
Okay. So you asked if the boat tail is going to be.
Okay, put your motor case down for a minute and just hold your boat tail up so I can describe what I'm looking for. Your boat tail is wide at one end where it attaches to the back end of the airframe, and it's narrow at the other end where the exhaust of the rocket comes out. Correct?
That's correct.
Okay. Now, is the back end of your motor going to be up tight against the back end of the airframe so that the flame is going down through the tail cone? Or is the motor going to be installed at the far end, the small end of the tail cone, so that the flame all goes out the back end of the rocket and doesn't interfere with the tail cone itself?
No, actually, it is designed that the flames that comes out of the motor goes through this part of the boat tail. Actually, as we mentioned in the presentation, the boat tail is designed to be frangible. This means that this is going to, this part of the boat tail is going to be consumed during the motor lifts.
What's it made of, please? What's it made of, guys? What's the boat tail made of?
The boat tail is going to be made of natural fibers such as jute, and we're going to use fiberglass.
So what you're telling me is that the back end of your rocket is going to be on fire as it comes down, right? Because your motor is going to set your boat tail on.
Hi. Can you hear us?
Yeah.
Okay, so before the session was expired, you said, well, you asked a question if as soon as the rocket is going up, if there's going to be a flame at the bottom of it because of the.
That's right. Make sure that you guys are recording this as well.
Should we wait for Rob?
We can give him a minute or two. He emailed me, so he may. Let me see if he can get back. We can give him another minute or two, and then if not, because he emailed me right as soon as the call ended that will work, that he can follow up with you guys. But so we don't necessarily have to wait for him. But go ahead and explain what you were gonna say.
Okay, so what I would like to tell you is that I understood that Rob said that when the rocket is going up and the flames is going through the bow tail, if the flames are going to propagate to the rest of the rocket. And we did a flammability test with the materials that we are using with the bow tail, and we found out that it is going to be burning, but there's not going to be flames. And as soon as the motor finishes the combustion, the flames are not going to propagate. They're going to end.
Okay. And so that's going to be a challenge for you. And why the reason why I say that is because fire is a big concern. And that's one reason why we no longer allow LiPos, because the LiPo batteries can catch fire very easily, especially if the rocket crashes. They can catch fire and start a fire. And so you might have take some video or some other evidence to show what will happen when it's actually in flight. But I'm concerned that if you get to the review and the safety reviewer is there and they ask and you know in advance that it's going to catch fire, they may say you cannot fly with it. So the simple solution, which I know is a challenge, is just to make it shorter, right? If you make it shorter, which I understand that affects all the design work you did, and I appreciated the amount of effort that you guys put into the analysis and everything, but none of that matters if you get there and someone says you can't fly it because it is a fire danger. Okay. So maybe you can add like an aluminum lining on the inside to prevent fire, or some ablative coating or something. So either A, you can show that it's not going to catch on fire, or B, you can show to whoever looks at it, hey, here's a video we have when it burns, look, it goes out immediately. Or C, you'll have to cut it shorter so that it is out of the flame path and can't catch on fire. Okay. And I don't, it's much better to find out this now, right, than when you're standing there 2 days from trying to launch your rocket. Because now you still have time to figure out what a good solution is to solve it so that it's not a safety concern. And again, it's not a concern of the rocket damage, coming apart, but one of the things that we've been tasked with, and especially me as the launch director, in terms of getting all these rockets up in the air, is the danger of fire. And so and that's a big deal. They really want us to make sure we minimize that. And so I just, when you said frangible before, I missed, because frangible means things can break apart easily. But now I understand what you mean, that it's consumable and designed to kind of be consumed in flight. And I actually had that happen to me with aluminum tail cones, where the aluminum actually is melted by the flame, but that's not going to catch on fire, right? So now that you've kind of heard both my concern and Rob's concern that we don't want the tail cone on fire, even though it might go out right away, the safety reviewers might go, well, still, I don't know. And so just either come up with a lining to prevent it from catching on fire. And I don't know if like a thin layer of aluminum, like just some aluminum sheet that fits inside will work, or something else, or do some more testing with similar material to see what happens when it is exposed, or worst case is cut it shorter so that it's not impinged by the flame and doesn't burn.
Okay, thank you so much. Really appreciate the feedback on that. And of course, we're going to come up with a solution for this, just to avoid this case that the boat tail gets on fire. So we avoid any kind of accident.
Yeah, and the other concern I have is I want you guys to get there and to be able to fly without a lot of problems. And so I don't want someone at the last minute to say, nope, you got to take the boat tail off, or whatever, and that causes other issues. So if you can start working on it now, that means when you get there, it won't be an issue, and you'll have a good handle on it.
Okay, thank you so much.
Yeah. Let me just, since I got you back, let me double check and make sure I didn't miss anything else. I think at the very end we covered. Nope, I think that's it. You guys did a great job of covering all the stuff in your presentation, and then being able to, see the rocket. And I'm really anxious to see the rocket in person because it's unlike any other rocket I've ever seen. So I'm excited to see it, and I look forward to seeing you guys in about a month. It's not much time anymore. So
we're a month far from the competition. Today's 17, right?
Yeah, it is. Exactly. Yeah. And there's still a lot of stuff. Yeah. Yeah. So, okay. Well, good. Well, all right. I think that's it. I think I'll email Rob and let him know that I had a chat with you. And I think he'll probably follow up with you via email just to kind of check to see where you guys are. But I think we're in good shape.
Okay. Thank you so much. We're looking forward to see you at the competition in a month.
Okay.
Thank you so much.
Sounds good, y'all. Thank you. All right. See you in a month. Bye-bye.